Okay. Good morning, good afternoon, or good evening, depending on where you are in the world. Welcome to today's R Medicine webinar, Containerization and R for Reproducibility and More, brought to you by the R Consortium. The R Consortium works with and supports key organizations developing R infrastructure through grants and sponsorships worldwide. Please visit our website to learn all the details and how your organization can become a member. My name is Jesse Kasman, today's moderator. I have just a few housekeeping items first. This webinar has a interactive Q&A section at the end. You're probably familiar with the Q&A button down at the bottom. Press that and enter your questions. And near the end of the webinar, we'll try to answer as many of your questions as we have time for. Also, the R Consortium regularly does R-related webinars. We have two in December that are focused on R and finance. Please check our website. The webinars come out regularly, and we'd love it if you participated. All right, so before we dig in, we have just a little bit of information that I wanted to include. Emily Zabor is associate staff at the Cleveland Clinic in the Department of Quantitative Health Sciences at the Taussig Cancer Institute. She's going to give us just a little information about R Medicine 2025, which you should be attending. Emily, you've got maybe some more details for us?
Great, thanks. Yeah, thank you to everyone for being here today. We're excited to be hosting this webinar as part of R Medicine and hosted by the R Consortium. And just wanted to make the official announcement that the 2025 R Medicine Conference will be happening June 10th through 13th next year. So this year it will be, this coming year, it'll be a 4-day virtual event. So there will be 2 days of demos and workshops followed by 2 days of talks. So a similar format to the past couple of years, but a 4-day virtual event. So we hope to see you all there. Please check out the website, which I'll drop in the chat a little bit later so that everyone can have access to it to get some more information and to see dates and other important updates as we post them.
That's
Thanks.
great. Thanks, Emily. All right, I'll do introduction now. Noam Ross is a computational disease ecologist and the executive director of rOpenSci, a nonprofit dedicated to promoting open science and validating data science and computational methods. He's a core member of the Rocker project, which took me much too long to put together. Docker, Rocker, I see the connection now. The Rocker project maintains standardized containers for the R computer language for R. So, Noam, thanks. Please take it away.
All right. Thank you very much. And thank you, everybody who has joined today. I'm glad to be here. Both the consortium and the R Medicine group have done like really great things for the R and statistics and data science communities. And I'm happy to be part of that work. So let me just share my screen here. Right. Get a thumbs up from folks that they can see what I'm presenting here. Here's my title slide. So I'm going to talk about containerization for reproducibility and more. But and you've already gotten a bit of an introduction to me, and I'll give a little expansion of that and explaining sort of like why I came to be working in sort of the containerization side of this work and why it's relevant to the type of analytical work that I do, and then why it'd be relevant for people in medical and clinical analytical work. So I'm a disease ecologist by training and by practice. I at times have and can be found wearing a Tyvek suit and spelunking into a cave to look at viruses in bats and other wildlife, but most of the time I'm on the computational side of that work. And so I do spatiotemporal analysis, sort of theoretical and simulation analysis, and applied work in outbreak forecasting in disease. And I run a team of people who do that type of work, and we need to collaborate in on a sort of a common platform. So that's one hat that brings me to this. Second, I'm executive director for rOpenSci. rOpenSci's goal is to promote open science and using our language as a tool for that. And so one of the things we try to do is develop tools and develop approaches and guidance for people to uh, do open science in a way that can be shared and built upon by others. And then one smaller hat that I wear is I'm part of the Rocker project team. Rocker is a project by one of the OpenSci co-founders called Bediger, Dirk Edelbatel, who's a longtime developer, especially in the R finance community, but of a lot of core R infrastructure, and Shima Tatsuya, who I've never known in any way except for his avatar. I've never actually met him in person, so you have to just go with this bush hen, essentially, which is what he presents himself as, but is a big volunteer in that project. And what we collectively do is develop and maintain standardized containers for R so they can be used as the underlying platform for people who are doing either analytical work that they need to share in common environments or software development work that requires a common development platform that they can use what we develop as a shared common environment. Today, I'm going to be giving a pretty high level talk on containerization. My goals today are to give a little bit of explanation of what containers are, but thinking primarily of this audience and the general audience as people who are more towards the researcher side of the spectrum, people who are in statistics, clinical research, medical research, whose main focus is working on the data, the statistics, and the analysis, and whose own goal is not necessarily to be doing the software development or the engineering of the platforms within which we do that. So the idea here is for me to talk about where and why containers are relevant for people doing that type of analytical work. So you can figure out where to plug in to those things, where to draw on additional resources. And so you can have a common vocabulary when you are talking with your system admins, with your administrators, with the engineers and software developers who you collaborate to think about, okay, where's an appropriate use of containers, and should I draw on more resources to learn, or should I be drawing on support for one of my partners to be working on this? So there will be less of the detail of exactly, the underlying technology of containers, or even necessarily like the how-to bit by bit, but try and give you a framework to say, okay, here's a way and a place and an approach for using containers that's relevant to the work that I'm doing. I try to be consistent, but I will often end up mixing up the term uh, Docker and containers, or Docker containers. Docker is the Xerox of containers. It's by far the most common framework for them, but it's a single one. I can briefly get into what some of the alternatives are, but 90% of you will be working with them will be working with using Docker for your container needs. And you can 90% of the time, that's just a fine way to go. Obviously, our own project, Rocker, is a Docker-based one, but there are other options out there as well. Probably one that's really actually relevant for the day-to-day user, and I'll get to that at the end. So, while today's topic is not specifically how containers work, A great place to start for that, and I'll just encourage people to use as a resource. If you're interested in at sort of a low level and you're someone who wants to really like build up your knowledge of this from like what are the like low level pieces and how do I connect this to how my computer works and how systems work. Julia Evans has an absolute spectacular introduction. Julia Evans creates these series of zines or comics about computing concepts. And so she also has a great one for Git, which is, say, relevant for a lot of people here, but then other ones on topics like networking. And so she has one of these on how containers work and how containers are constructed out of the low-level pieces of an operating system. And so if you're interested in it in that level, I'd encourage you to go there. I'm only going to have really like one slide about what containers are and how they work, and that's this. At a high level, I think of containers as a lightweight framework for having isolated but linkable compute environments. The isolated part is very important for, say, concepts of reproducibility in the context of things like data science and statistics. And linkable is also important in terms of resources. You will note that reproducible is not sort of a part of the container definition. It is something that we can use containers to try to achieve reproducibility goals, but they are not just because you use a container doesn't mean that your work is reproducible or archival. They're one tool that we can use towards that goal. Containers are let's say, sort of 25-ish year old technology, really burst on the scene 15, 20 years ago in terms of the being a core technology of how the web and internet services were powered. And they are an evolution from the concept of virtual machines. So in this illustration I have here, we have virtual machines and containers. And there's really sort of a couple of important differences between them. So a virtual machine is something you may have used if, for instance, you have a computer that you've run something called Parallels on because you want to run Windows on a Mac computer or Linux on a Windows computer. There's a thing called a Linux subsystem. That is a virtual machine. Essentially, it is a whole copy of a computer inside your computer. And a virtual machine represents an operating system, then all the binaries and libraries and software installed in that operating system. And then on top of those things, you can have the tools you're actually using. So your R scripts, your interactive environment, such as RStudio or VS Code, and you have a fully isolated whole computer copy of which within a computer down from the operating system. And then there's the underlying hardware that supports it. And you can run multiple virtual machines on a computer, although it's all very resource intensive to do so because each one has its own RAM, each one occupies its own component of your processor. And so they are very useful. But the container technology that came along said we can do this in a much more lightweight way rather than having a whole operating system and a whole computer that are completely separated from each other. We can keep the host operating system and share that between computers. The core part of that operating system or the kernel is something that is shared by all containers. And then Docker or the container orchestrator then assembles containers out of pieces that can be shared. So you can have a layer of files that are shared amongst multiple containers. So let's say your R installation is something that is shared amongst multiple containers. And then there can be things that are separate. So in one container has the same base R environment, but it has one set of packages installed. And then in another container, there's a different set of R packages installed, and those are used for different analyses. But they are sharing resources. They can share memory, but because of the careful orchestration, there's a maintenance of separation between any processes. So permissions prevent things from running into each other. And this was key in containerization as a technology for the web because it meant that you could deploy many, many containers and they would only occupy the resources they needed, which allowed one to spin up and scale services in a way that one couldn't before. So That's really all you need to know about sort of the underlying structure of containers. There's a bare minimum of vocabulary and things that should be distinguished that I want to get into between sort of the different ways we talk about the containers themselves. So first, there's the idea of an image. So an image is everything that goes into a container. It's essentially a collection of files and a collection of specifications of how those are linked together that are put together in a package. And so an image is just essentially a zip file that you can pass around between computers, that you can share on the web, that is something that you can store alongside your analysis that defines the whole container and its working environment. And then the container is the running instance of that image. So the image is the container at rest, but then you can take one image and launch as many containers as you want off of it. So that's useful in the, services context. You can launch more containers as you need more capacity, but also you can have one image and you can run different analyses in different copies of that image, even though you only need one image at the same time. Then there's a word that there's not actually a good generic version for, so Docker has come to define it, Docker file. And a Docker file is a simple text file that has the series of commands to define the image. I'll show you an example of that in a minute, but it's really that minimum specification. It says, here's what I want the image to be based on, and here are the things that I want to be copied or installed or configured in it. So it's essentially your configuration or specification that defines that whole environment. And then we have image repositories. There are a number of different image repositories, the most common one being Docker Hub, and that is a place where at a large scale or at a small scale, people can deposit and share images so that you can exchange them amongst each other. Now, the main context that a data analyst will think of containers in is as the idea of having a type of fixed working environment. So when you have a set of analyses you are doing, you may within a container have everything that you need to perform that analysis. And so that container can be isolated from other work that is going on that has different requirements, from your day-to-day computer, which you may be updating or changing things on a regular basis that you don't want to change specific to that analysis. And then that fixed working environment can be defined in such a way that other people can spin it up in the exact same way. This is probably, when we think of reproducibility, the main framework that we think of. And I especially like to think of containers as part of a broader framework of what I call layered reproducibility. Reproducibility is not a fixed or a binary thing. You can have work that is more or less reproducible. And I tend to think of that in this idea of nested layers. It can be an onion or a Russian nesting doll, which you can think of, which is less likely to make you cry. But it kind of goes from the core, which is where you have the things that an analyst is spending most of their time on, which is the data that is part of your analysis and the code that you are running on that analysis. And that's sort of the core bit of what you're doing that you want to be able to transfer among to others. And then as you move to other layers, you often get to the parts that you want to be thinking about less, right? And that we would like to simplify the process of standardizing and moving around. So when there's code and data, then you have the aspect of the workflow. So how do you link together the different analyses that you have, the different files? There's an order and an organization that they have to go into. And so there's that workflow layer. Then beyond that, especially in an R environment, you have your software packages. You have the tools that you are using to run that to load in your code, to run on your data that your code works with, that you often are getting from somewhere else. So these are in the context of R packages that you're installing, but also if you are running in, SAS or Stata or Python, right? Those are like your core dependencies that you're working on. And then the dependencies themselves might be sufficient for running things on your computer, if you were to define, say, okay, this is the set of packages and this is the versions of the package that I'd use, but they are built upon our system dependencies. And the operating system and the system dependencies are like required to run the packages that run your code. And often they are much more obscure and abstract, but they can have a big effect. For instance, your operating system might have its own linear algebra solver library in it, and that's something that your R code draws upon, and you probably may not even realize that it's doing that because it's wrapped up inside, say, your linear regression routines. But those solvers can be different from version to version when you update software or update your operating system. And so those are something that can make a difference numerically in your analysis, and so they have to be considered. Then there's the operating system itself, and there may be differences because between operating systems in which packages work. And then beyond that, there's the hardware. So hardware, be it the CPUs or the GPUs or the other components they were running everything on, is also an important component. And all of these together are the layers required for reproducibility. In an R context, your R code and your scripts and your data files are where the code is, and then the workflow can be defined with a number of different tools. For instance, you might be using an R Markdown or Quarto approach to put all the pieces together. You might be using a tool like Targets, which is a common framework in R for linking together lots of different steps of an analysis, or something like Makefiles, which do something similar. And then the sort of packages, system dependencies, and operating system layer is what containers can support. So you might be using something like Rn to define the packages you're using and their versions, but containers sort of cover those three layers and can abstract away a lot of that challenge from sort of operating system through packages. I do note that they don't solve the hardware problem. And one of the real challenges in working in containers, especially the last few years, has been the proliferation of new hardware that has to be thought about. So especially in machine learning contexts, there's a lot of different GPUs, and how you build your containers is downstream of the GPUs. Also, if some of you, say, have Apple computers that have come out in the past 4 years, they have a new popular architecture for their chips, which means that we have to define containers that are specific to either that overall architecture, which is called ARM, that is now more and more entering into sort of consumer normal hardware. Um, but containers can cover a wide swath of this component. And the part of that they can cover is this. So this is the README from a code repository for a paper that I wrote quite some time ago. It was a very long time ago, actually, such that I had used an old framework called PackRat to manage our dependencies. But then I said, okay, we've defined all these dependencies, but in addition, you have to have all of these things installed, right, under this version of R and this operating system, and that's what we use to run this program, and we could come out with different results if you have a different version or different types of software than uh, what I wrote down here. And this was not very specific. It just said you need to have all of these things. I didn't have a good definition of where to get them or what their versions were. And so if someone didn't sort of have all these tools or at their ready for themselves, it would be sort of quite an operation to try to put together this analysis again and do it. So an example of how this can work a little differently in a container context, I'll pull up an example from my colleague Carl Bettiger. So Carl has yet another analysis that he has on GitHub here, which is called Bad Forecast, Good Decision, which we use in sort of natural resource economics, essentially looking at how one can set up decision frameworks that are robust to environmental forecasts that have challenges. And within this, he has one Docker file defined that's just a few lines of code. And the bulk of it is this first line at the top that just says, we're going to define this Docker file as being derived from somebody else's Docker image. In this case, the Rocker project has an image, which they call the binder image, which I'll get to in a second, and it runs R 4.1.3. And this file just runs a few lines that copies over the files that are in the analysis, just defines the user that can access them, and then runs one line of R code restore, which installs all the R packages that use the renv tool. So this is the only thing in the repository he has here, which includes all the data and the manuscript and the different R scripts that run the code that define the Docker image. But by putting this one little bit in there, one can make this transferable. So for instance, there's a great service called Binder that's run by the people who maintain the Jupyter Notebook framework. 2i2c is the organization that's based out of Berkeley. And if you just give it say a GitHub repository link, it will launch and run your analysis based on the fact that you have a Docker file in there that defines the image. So I could punch in Carl's the URL of Carl's analysis here, and the first thing that it will do is it will run that Docker file and say, okay, we're going to fetch that original image that you want and run those few lines of code, right? And then we will have a working environment with all of the same things that Carl used to build his analysis. So the main function here of the Docker file here then is just then to define a compute environment, define a place within you can run your code that can be transferred to another place. And in many contexts, especially here, can often just be run on the internet in the cloud. People don't need to install anything on their machines using a service such as Binder, and then there are other ones such as GitHub Codespaces. You can simply fire up the container and anyone can run your analysis using the exact same pieces of your layered reproducibility as you have. An extension of the environment is something called a dev container. So Docker files will define sort of all the software that you want to run, say, an analysis. But often when you are working on analysis and you are collaborating on analysis, you don't want just the software that's required to run it, but you probably have a lot of other tools that are important to you. You might have RStudio and RStudio add-ins that you use for keyboard shortcuts. You might have something that you use to explore data interactively. And the idea of a dev container is to set up a container that not only can run your code, but can be useful to work with. And there's a common specification for dev containers, and also the Rocker project provides what we call dev container features. So with a dev container, you can define a standard image, and then you can say add image features that are published by other dev container creators. So here there's a standard, say, container that's used essentially across everything on GitHub, right, that Microsoft runs. And we're going to say we're going to add a Rocker feature to it. So what that enables one to do is have an interactive coding environment. So for instance, there's this group EpiNowcast that I really like the work they do. They're based in the UK, and they built a series of tools starting during the COVID pandemic that they're using for a variety of different outbreak analytic contexts that essentially does real-time forecasting of epidemic growth. And so they will have an R package that they've set up called EpiNowcast, and it has this little dev container folder that contains a file like this, which says everyone's going to work off of a container that is defined by this basis and then Rocker's additional R installation tools. And the neat thing about that is if you go to them on GitHub, you can just click this little code button, and rather than downloading anything, you can launch a code space that will make use of that dev container specification. And it will either on the web, or if you have a IDE that's connected to GitHub, launch the exact same environment that everybody else is working in. So in addition to the files, what happens is that as soon as that's launched, all of the contents of the dev container are run, which install all the additional components, which are both, say, the settings of how people are working. So, they might have rules of how the IDE is using tabs instead of spaces or something like that, and they're all doing that consistently. But also all of the development tools that they have, including, say, adding some documentation files, are added to this container. And as soon as one pushes that button, you have a common environment to work in. So the broad idea here is that you are wrapping your work in a common specification that goes all the way down to the operating system level. As an R user and R developer, there are a number of different tools that are out there that let you sort of abstract the way of defining what that container or Docker image is that you're creating. And so I'm going to refer to a couple of them here. So this is great package by Daniel Nust called Containerit, and it will take 3 lines of code to produce a Docker file that defines everything that is required to work in your environment. So if you are actively working on analysis, you can use Containerit to run a quick command of, say, create a Docker file based on the current session info of what I'm working in now. And what it will do is it'll take that session info and generate one of these Docker file specifications that says, okay, the current running version of R is 3.4.4, so we're going to build a container based on that. I'll use your username to give a tag to it, and then we'll look at all the things that you currently have installed on your computer and include them in the dependencies that are required, and then install all of the packages that you currently have loaded as well, be they CRAN packages or ones from GitHub. And so then that Docker file is ready to use in any of these services, or someone else can spin up and build a container based on it. There's another very similar tool called Lifter that's specific to R Markdown or Quarto documents, and it just requires that you add a couple of additional lines to your R Markdown or Quarto header that say, do you want some additional things installed? Are there any system dependencies you're adding? And are there packages from CRAN or Bioconductor or remote from GitHub that you are installing? And it will, upon knitting the document, also produce the Docker container that is required to run that. And so when you share that document, you are sharing the specification of everything down to the operating system required to run it. So one of the things you have to think about in this is what the requirements are for making your containers reproducible. A Docker file or a dev container file is just a text file specifying the image to be built, but it may not build it reproducibly. They have to be produced in a way that should be. So if there's a command in your Docker file that says install a package down from GitHub, you could say install the latest version, and then every time you run your Docker file, it will get the latest version of the package. Or you can specify, as in this case, a specific commit or a specific version, so that when you run your package version, your Docker file and produce that image, it will be the same every time. And that main consideration of making sure your Docker files are specified in such a way that they do not change over time is sort of the core thing in the design of images that we produce at Rocker. We have a series of different what we call image stacks, which are differently designed series of images. And the core ones that we use are called the R-ver images for R versions. And what these images are ones that remain absolutely static as we release each version of R. So you can install a copy of R-ver for any version of R going back to 3, essentially. And for each version, every single package that will be installed in that is the date specific one from when that was the version of R that was being used. And then we have a series of layers. You can have a basic package that just installs R, or it can add RStudio on top of it, or it can add the tidyverse on top of RStudio, or it can add everything you need for Quarto and R Markdown, or geospatial dependencies, or the dependencies required to run something on the web on Binder, or required to run on Shiny. And every one of these is tagged. So you can say, I want R version 4.1.2, and every package that will come along will be the ones that were available when R 4.1.2 was running. And so that stability is the core thing that we try to maintain within these images in the Rocker project. And when you are building for sustainability, that's the kind of thing that you want. The other thing that you can do is that once you produce an image, that image can be saved and it can be stored in a repository. It can be stored alongside your code, be it in a submission for a regulatory analysis, for a submission to a journal, or in your deposit for, say, a long-term scientific repository. You can save the image rather than just the Docker file, and that will remain absolutely static, and everything will run the same way in the future with your code if you have that alongside. This is not the only framework for R based containers, and so a pretty common other one that people use is for rapid testing environments. And this is especially relevant for people who, say, are developing R packages. So when you're a package developer or other software or tool developer, you often use continuous integration, where you are rapidly running a series of tests every time you make a change to your code. And one thing you can do in order to do that is say, okay, what is the environment in which we're running those tests? So every continuous integration platform, be it GitHub or GitLab, or one that I use here called Circle CI, has some place where you can say, what image do I want to run these tests in? And so in this case, there's a tool that we have in rOpenSci called Tick, and it runs on a platform called Circle. And there's just like a little specification in the testing environment that says run all of these in the Rocker verse image. In this case, we don't specify a version because we want always the latest one, because we're continually developing software and we want to test against the newest version. And there are different considerations for that. So rather than things being static, we also want them to be fast, because when you are developing a piece of software, you are running a test every time you make a little change. So this is just a little log of a recent developer who's working on this package, and they might be, running change after change after change, and they want all the tests to run quickly so they can get feedback. So these are tests that run in just a couple of minutes or down to a single minute. And often what is the barrier to getting that happen quickly is the time it takes to spin up the testing environment. And so we have a series of containers that are more optimized for that purpose. So Rocker has a series of containers called rbase, and then derivatives of that that are based around having the most recent and the most rapidly installable uh, stack possible. So Dirk Edelbatel leads the development of these. And so tools like RBase, but then also RBSPM and R2U have pre-built binaries for all the packages linked with them. So when you spin them up in order to run a test, unlike, say, an analysis environment that you might keep open, the test one you're tearing down and spinning up, so it's exactly the same every time you run the test. These are designed so they can run really fast. Also, outside of the Rocker organization, our hub, which is another project of our consortium, which Gabor Sardi leads, also has a series of containers also for testing. And these are designed to be as similar as CRAN is as possible. CRAN itself doesn't run containers, so it's a lot of effort to try to reconstruct the CRAN environment. Uh, but they have a series of containers that are specifically designed to imitate CRAN's computers that they use for testing. And so in addition to being fast, you want these to be good matches, and they run these. So these are containers you can use for that purpose. Beyond testing, you start getting to a wide variety of other applications for containers. So you might be running large scale analyses, big Bayesian things, big data things that need to be deployed to worker machines in other contexts. So you might be sending code to Amazon Web Services or Google Cloud or GitHub runners. And people are using that because you have some large scale analysis that needs to be done. Maybe you're doing large scale Bayesian simulation studies. Maybe you have a very large data set that needs to be requires those kinds of resources. These all essentially will be using containers by default, whether you know it or not. So if you're using Amazon, you might use a package called lambda-r that runs the Amazon in the Amazon Lambda tools, or similar, there's one for Google Cloud runners. And both of these packages inside will pack up your code in a Rocker-based Docker container before it sends it off to Amazon and Google Cloud. Or rather, it will tell Amazon or Google Cloud, grab the Rocker container so that when I run my code in the cloud, it's a common environment across all of them. One, you probably will be using the Rocker ones, but Posit or our studio actually have specific images that they publish for this purpose as well, because they have their own sort of cloud compute. So if you are using what is now, I believe, called Posit Workbench, or the other RStudio tools that let you launch and run a job on other cloud-based or local infrastructure, they are packaging them up in these specific containers. And if you are using those for some other purpose, you can grab from Posit or RStudio the containers that they define that are specific to our workbench, right? And so, that means that you can move tools. Maybe you're moving to different infrastructure, and maybe you used our workbench before and now you're using something else, but you can make sure that your jobs run in the exact same containers that they defined as they published. Then an entire sort of other category of why you might use Docker as an R user is, rather than trying to package up your R code, there is other code in other languages that need to be packaged up in a runnable environment that aren't necessarily installed on the same machines. And you might want to run some things that, rather than trying to figure out how to get them installed locally, because they may not be compatible with your R setup or otherwise, you can just run them inside a Docker container and maybe use R as an orchestration approach. So one version of that is that you might have something where you launch a sort of a service worker, like a container that's going to do things, and you'll send commands back and forth. So if you're doing web scraping, you can launch a web scraper server called Selenium, and run the R Selenium package, which when it runs commands, will send commands to that server. You can do the same thing for a tool called the open source routing machine. Open source routing machine is essentially a local service that does Google Maps like direction generation, so routing from one location to another. And so it will run in a Docker container, and the ROSRM package will simply send commands to that container or back. The H2O framework for machine learning does something similar. They have a machine learning sort of whole package container, which can run on your computer, or maybe is running on cloud architecture, and the H2R package sends commands back and forth. So that's a different way. Rather than wrapping your analysis, you are going to be wrapping a subtool of your analysis. There's actually a really great presentation on this by Joel Nita in the context of bioinformatics. So um, he talks about lots of different command line tools in bioinformatics that are used for, genomics processing that themselves don't run in R, and you have to like connect to the command line, but they themselves are challenging to maintain and to install. And so he has a great tutorial on how you can use the R targets framework with Docker. So you can say, okay, I need to run um, a alignment program for all of these FASTA files for genetics that I have. I'm just going to run a Docker command to run that in a containerized version of the program rather than trying to get that program installed on my machine. If I have Docker on my machine, I can run it without thinking at all about what the installation requirements are of that. And he has a really great framework. We also actually had a webinar, and that's also linked from his webpage. And then finally, you might be using Docker for the common approach of serving something on the web. Maybe you've built a tool, a Shiny app, a plumber service. Your model is something that is being used for decision making elsewhere. And in that case, you may be running that Shiny app within a Docker container, and the people who are running web services and your IT infrastructure will probably much prefer you just handing them a Docker container that contains the program so they can link it up with everything rather than they themselves trying to manage your dependencies. And that's something that can use the resources we have at Rocker as well, be it running a Shiny app or a Plumber API, or even serving a development environment such as RStudio or Jupyter as an interactive web service. When you're doing that, you might consider yet another set of images. Our hub has a set of images called R minimal that are really designed for the idea of them being small and therefore easy to spin up and scale. So if you are running an API that is supporting a model that you've developed, R minimal is potentially a good option in that what it does is it strips out everything but what is needed to run the program. So as opposed to, say, the Rocker R stack, which has everything in a development environment it requires, that has RStudio installed, or a dev container that has all of these extra tools. This strips out even the documentation from R. So the documentation files aren't there. There's nothing there but what is required to run the small set of packages that you define. And so while other images might be several gigabytes large, you can run R minimal things which are just a few megabytes in size. And that means that if it's being run as a web service, it can easily be spun up and scaled. So if you are developing something that is going to be used, say, at the hospital or larger scale, you might look to images that are of this sort. I am going to stop there for additional questions. I actually have a bunch of other slides and things that I could talk about here, but I want to make sure that we have a little bit of time for people to ask about any of the things I've covered or any of the things that I haven't covered. So thank you very much, and please let me know what else I can make clear.
Noam, thanks very much. That was fantastic. Everyone, if you use the Q&A button at the bottom of the screen, you can enter your questions. We'll take a few questions here. Noam, we already have a couple that have come in during the webinar, so I'll read them out loud and maybe you can respond to them.
Great.
So this is from Anonymous. How to share a containerized project with someone who is relatively low tech / new to R. What do they need to know? What do they need to do to run the project, see results?
So I'd say if you have a project and you have managed to set it up and containerize it, you have a Docker file that defines what's there, you know what's running, and you want to make it as low effort as possible for them. Uh, the best thing to do is use one of the online services that just launch a Docker container. Like then they don't even have to install Docker on their machine, right? So you can go to mybinder.org. There's a little documentation there, but you just need like a little other specification of what you need in your Docker file. So that, because what will happen when this runs is that you can choose whether it will launch a RStudio instance or a Jupyter notebook um, of your analysis. And so that will just pop up in the browser for them. If they were a little more technical, I would advocate for the GitHub version of the same thing, right? But partially because that launches a VS Code environment, which is a little less common for people, and also because it's like the dev container specification is a little more complex, like it's one notch higher. But then there are several other services. There's one called Gitpod that essentially does the same thing. And so I'd say the best way to share it is do it so that like the cloud infrastructure takes care of it, right? Once they've done, if they're really into it, then you'd be like, okay, you want to install on your machine? Well, we'll point them, go to docker.org, and there's the installation instructions, and here's 3 lines of code, hopefully to get it up if you have that. But I would start with this because it reduces the friction for people to get a development environment working.
Okay, awesome. We'll go on to the next one. Is GitHub Runner an example of a container?
Not quite. So the GitHub runners um, are basically virtual machines. And then people run Docker containers within those virtual machines, right? So they have, I mean, almost everything you encounter in the cloud is a virtual machine, whether you do it or not. You have a web host, you have a different thing. The vast majority of it are virtual machines, like at the base level, right? Unless you're like going to some provider that says we are giving you a bare metal machine of this exact size, right? Like Amazon instances, they're all virtual machines, and that's the setup. And then I'd say like, a very large fraction of GitHub actions are defined by the container that they're in. So be it an action that you write yourself or an action that you import, usually they just have a Docker container that says what all the software is required to run that action.
Okay, thank you. We've got a couple, two, three more. This is from Andreas. Say I really just want to use Docker for reproducibility. What is the
Mhm.
recommended workflow? Program the analysis first and wrap it up at the end, or set up the container at the beginning and develop already within the container?
I mean, it really depends. I always advocate for what's going to be the fastest spin up for people. And right, like it will be faster to get started without it until you are used to things. And especially in the early stages of an analysis, you tend to be um like changing your mind as to what tool and like what packages and what versions you're going to be doing things a lot. And so I actually often don't get around to like Dockerizing or setting that reusability until things have stabilized a little bit, right? Just because like uh the iteration is much faster at that point. Like the installation steps that happen each point can take a little while. So I tend to put it somewhere in the middle, right? Like once I have a good idea of like what the structure of the whole thing is going to look like, unless I'm in a framework to do it differently. So um, with my recent team that I've worked for a while, we have our own high performance servers, and we actually sort of pre-set up a Docker environment within them. So everyone who logs on those services, it's already a Dockerized environment. We already know what the pieces are. And so it's very like most people on the team didn't know anything about Docker and didn't need to. And when it was time to wrap up their analysis, we already had the specification of the container they were working in, right? So we could just export everything from there. And again, like it's definitely something that, it depends on how much you want to take on, whether this is something that your organization should be handled by the individual, analyst or, the research software engineers within the team, are whether they should be the ones who are sort of helping everyone just sort of have these environments good to go.
Okay, excellent. Next one is from Jaren. Can you describe scenarios where Docker containerization might not be appropriate? For scenarios that apply, what solution would you recommend instead?
Yeah, definitely. So, I mean, the thing is, when I get at this layered reproducibility aspect, right, as things become more complete, they become less flexible, right? So, if you are making something that needs to operate in a lot of different environments, then you want to make sure it works beyond just the container that you have specified. Um, when we are doing testing of our packages from CRAN to GitHub and other things, they are generally being run on different hardware and in multiple different containers for rapid testing, right? But because an R package itself is a tool that is designed that ideally should work on whatever kind of computer that people run. It's one of the great things about the R ecosystem. Everything is tested across, Linux and Windows and Mac, and you want a tool that is robust to that. So in that case, you can use containerization to test across those environments, but you want the tool that you are sharing to have been built to be robust to different environments. And so the sort of the solution that is often the case there is, you know, doing your testing in such a way that is looking at a lot of different environments so that your tool is ready for whatever is being thrown at it.
All right, excellent. Um, all right, we have one from Stas. What are the appropriate ways to specify a set of package versions? In the good old days, it was MRAN dated mirror. Is POSIT public package manager an appropriate substitute these days?
I would generally say yes. Posit has taken that sort of, public infrastructure role um, from uh, from Emran. Bioconductor, for instance, they do their own snapshotting. So if you in the bioconductor context, they publish sort of fixed snapshots every 6 months. So the Rocker ecosystem draws on Posit Public Package Manager, right? So when we build Rocker version 4.2.3, we pull all the packages from Posit Public Package Manager uh, on the date that is actually defined. The image is defined as the last date that before the next R version came out. So if you grab 4.2.3, everything comes from Posit Package Manager on that day. We previously used Emran, and at this point, some of the other tools that are actually doing this as well are downstream of Posit Package Manager. So while that does mean the general ecosystem has a point of failure, right? Like I think it's a reasonably reliable one for some time. And then ultimately you can get everything off CRAN as well. It just means that you will have to build everything from source code, which means it takes a whole lot longer. Um, the best tool for specifying those packages I still is currently renv, essentially. So most of our Docker containers have an renv file in them to define what versions of packages and what dates should pull them down.
All right, we've got two more, if we can squeeze them in. From Anonymous, how have you used Docker in your line of work?
I mean, there's a lot of different ones. We've deployed analytical interactive tools from based off the models that we built for forecasting. I did COVID forecasting for New York State, and so we had a little a dashboard that was served as a Docker image. More commonly, right, like we have these in our most people wouldn't necessarily use Docker in like their day-to-day on like their sort of, in the analytical work they're doing on their machines. But as soon as we moved into our high performance compute environment, everything was wrapped up. And so we had our defined Docker images which were already running in our high performance compute. And so when you logged on and ran, you were inside that container. And then when we packaged up analyses that were done there, we just exported a copy of that container as well. Um, so it's a lot of different things, right? I've also used sort of Joel's bioinformatics. Let's use Docker as a way to avoid figuring out the installation issues of this one processing command line program. So it has a lot of applications across a lot of pieces of the analytical pipeline. Um, and then I see Andreas for the last question has in a reproducibility study. Can I comment on the relation to NICs? This has been I've long delayed learning properly about NICs, and I should do more because we have a NICs management package as a part of our OpenSci suite now. So Bruno, who's done a lot of the development of using NICs for R, has been doing stuff with our OpenSci on that front. Um, it's part of it's part of the onion layer, essentially, right? So, you can nix, also like is another way of covering like from here to here. It kind of depends because Nix is a little less of it. Nix because Nix you can run Nix on a Mac, and then GUIX is like a whole operating system itself. There's Nix on top of the operating system, and GUIX is Nix as the operating system. It covers a lot of the span, right? So if you are using Nix, you can use it to deal with a lot of those reproducibility challenges. It has a lot less wide adoption. So one of the challenges, if you're doing something in Nix and you want to share it with people who are not Nix users, probably you just want to use a Docker container you can just run your Nix commands in there and have a Nix operating system in a Docker container. And that will be a lot more likely to be able to be used by someone who isn't up for setting up Nix themselves, right? Like on their own machine. Um, so I'd say like it's not um like there's a lot of overlap in the applicability, right? Like Nix covers a lot of the things that Docker helps do, but also if you're going to run a web service that needs to scale, you probably also are going to if you're running it in Nix, you will probably put Nix in a Docker or similar container, right, for deployment. Um, so Nix covers most, but like not quite the bottom bit, not quite the interface sort of at the lowest level of the operating system for the most part. I think it is. But to be fair, I've never actually used Nix myself. I just sort of have like read some of the high level documentation for it.
All right, at that point, I think we'll finish up here. I want to thank everyone who came and participated and listened. We really appreciate it. Thanks very much, Noam. I really appreciate all the effort and time put into this, and Emily for the information on our medicine 2025. Everyone here listening, our medicine information is going to be coming out very soon, so please pay attention, and we'll let you know. And thank you very much from the R Consortium.
All right.
Thanks,
Thank you
everyone.
all.
Thanks,
Bye.
Noam.
Have a good evening.